So today we were going to continue talking about three-phase power systems, and I was going to introduce to you guys transformations that we could use to make any delta connected sources look like a Y connected source, and any delta connected loads look like a Y connected load, so that we could apply the single phase equivalent circuit that we learned at the end of our last class meeting to any three-phase system. Okay, so let's start by talking about our source transformation. So I'm going to start with a Y connected source. So here is our A phase voltage source, VAN. Here is our B phase voltage source, VBN. And here is our C phase voltage source, VCN. Like so. I'm going to just label this back node over here, my neutral terminal. And because we are converting into, or trying to learn how to convert into a delta connected voltage source, I'm not going to bother actually drawing out the bottom neutral conductor because we're not going to wind up using it. Because as we learned in our last class meeting, the delta connected source literally does not have a neutral connection for us to connect to. Okay. So just over here for context on the right-hand side of the page, I'm going to draw our delta connected source. So this is going to be our voltage source VCA. This will be our voltage VAB. And this will be our voltage VBC, like so. And what we're going, oh, sorry, this is terminal A, B, and C. And effectively, what we're going to do is to try to figure out what's going to make the voltage drops across the terminals of our networks the same. So I want to start with a voltage VAB measured between the A and B transmission line terminals of both our Y connected source and our delta connected source, like so. And we are literally just going to set these terminal voltages equal to each other. If we want these things to be electrically equivalent, we need to see the same voltage drop across the terminals of our networks, okay? So on the left-hand side, I can solve for that voltage VAB by simply applying Kirchhoff's voltage law around that topmost loop, okay? So I'm just going to indicate the path that I'm going to take. I'm going to start here, go across like so, down across those terminals, through the source, and I am done. Okay. So if I apply KVL around that path, what I would find is I would wind up having, so let's see, KVL at the gray path. I would wind up finding negative VAN plus VAB plus VBN is equal to 0. Rearranging this guy slightly, I would find that VAB is equal to VAN minus VBN. Okay. If I were to apply KVL to a similar gray path on this side, I would simply get that my terminal voltage so I would have something, sorry, that scrolled way too far. I would wind up getting negative VAB, so that's my source voltage, plus VAB, my terminal voltage, is equal to 0, and unsurprisingly, VAB is equal to VAB. So this is essentially me saying that the phase voltage and the line voltage for our delta connected source are the same thing, which we already knew from our last class meeting. So essentially, I now have an expression for the terminal voltages, VAB, in terms of my phase voltages on the left-hand side and my phase voltage on the right-hand side. And so I'm just going to set these guys equal to each other, okay? Perhaps it might be slightly more easy to follow what's going on if I used the green color. Let me just swap that out real quick so that we can see which one of these is representing those terminal voltages. So we actually already learned this transformation at the end of our last class meeting, right? So I can express VAN and VBN in terms of the same voltage because we know that in a balanced system, VBN is just VAN times 1 angle negative 120 degrees, right? So essentially, I could say that this is VAN times 1 minus 1 angle negative 120 degrees, which comes out to be VAN multiplied by the root 3 angle 30 degrees. I asked you guys to throw that into your calculator in our last class meeting, and you did find this result. So my terminal voltages, VAB, in green, are related to my phase voltage by a factor of root 3 angle 30 degrees. So if I want my terminal voltages on my delta connected source to be equal, that means essentially that to convert from a Y connected system to a delta connected system, I simply multiply by a factor of root 3 angle 30 degrees. Okay. So that's my transformation to go from a Y to delta. So how do you guys think I'm going to go from a delta to Y in the opposite direction? Divide by root 3 angle 30 degrees. Exactly right. So to go from a delta to Y, I would simply multiply by a factor of 1 over root 3 angle 30 degrees. So essentially, that conversion factor that we found that allowed us to transform from a phase voltage to a line voltage in a Y-connected system is the exact same conversion that allows us to convert from a delta to a Y, or excuse me, from a Y to a delta. And then if we simply divide by that conversion factor, we can go from delta to Y. So this is our source transformation process, and we've defined it in both ways. So any questions about this? And we'll put it into use here in a couple of minutes, and it might make a little bit more sense if you're not fully catching what I'm throwing just yet. Okay, so now let's talk about load transformation. And so this is the part where me not having my notes is going to be kind of sort of problematic. I'm going to have to gloss over some details, which I don't think that you guys are going to give a shit about anyway, because it's just a bunch of math. But I'll try to explain what's going on. Okay. So I'm going to start with a Y connected load here on the left-hand side. And let's say very explicitly that this is a balanced load. So all of these impedances will simply be ZY. And over here on the right-hand side, let's have a delta connected load. And let's say that they're all balanced so that every one of these impedances is going to look like Z delta. Like so. So what I'm going to do now is essentially I am going to try to find the equivalent impedance seen between those sets of terminals and set them equal to each other, right? So essentially, if I look in here between terminals A and B, I would see some impedance, ZAB. And if I look through this set of terminals, I will also see some impedance ZAB. Okay. So on the left-hand side, what would I see? Well, I think I see ZY in series with a second ZY, right? And I'm going to have that C phase impedance just kind of dangling there, not connected, okay? So it looks to me like I see 2ZY. On the right-hand side, what do I see? Well, I think I see a Z delta in parallel with two Z deltas in series. Does anybody else see that? So between the A and B terminals, I've got this guy directly, and then in parallel with that, I'm going to have these two guys added together. Okay. So that's going to look like Z delta multiplied by 2Z delta over Z delta plus 2Z delta like so. If I set these ZABs equal to each other, actually, let me go on and furl this thing out a little bit more. So Z delta times 2Z delta is going to look like 2Z delta squared. And Z delta plus 2Z delta is going to just look like 3Z delta. Everybody okay with that simplification? So if I set these guys equal to each other, and I'll just do this here in the middle, I would have ZA, or excuse me, ZAB is equal to twice zy is going to be equal to twice z delta squared over 3 z delta is once again equal to ZAB. Well, I think it's fairly obvious that 2z delta squared over 3z delta, I can just cancel out one of those factors of z delta, and that's leaving me with the relationship 2zy is equal to 2/3 z delta. And from this, we could say that zy is just 1/3 of z delta. Anybody have a problem with my algebra? So essentially, if I want to go from delta to y, I multiply by a factor of 1/3, right? Because we can see that z delta is just 1/3, excuse me, zy is just 1/3 of z delta. So I take my z delta, multiply it back by a factor of 1/3, and that gives me zy. So it stands to reason then that to go in the opposite direction, to convert from a y to a delta, I would simply multiply by a factor of 3. And so now I have our different transformations, right? I know how to transform a y-connected source into a delta-connected source, and a delta-connected source into a y-connected source. I know how to convert a y-connected load into a delta-connected load, and a delta-connected load into a y-connected load, assuming everything is balanced. So we now have our set of transformations that we can use to analyze any type of three-phase system and be able to convert it back into a YY system that we can apply our single-phase equivalent circuit to. So let's put this into practice by looking at our in-class assignment, okay? So in this first problem here, we have a balanced three-phase delta Y system. So just as a heads up, I think I've mentioned this before, but I just want to be super clear about it. Whenever I have a something something system, the first something is the source and the second something is the load. So I'm being told essentially that I have a delta connected source and a Y connected load in this system. I'm given line impedances and load impedances, and I'm also told what my line current is, and I'm asked to determine the phase voltages at my source, okay? So I'm going to draw a picture of my system. So I've got a balanced three-phase delta source, so that's going to look something like this. So here's VCA. Here's VAB. Here's VBC. And my ultimate goal is to solve for any one of those three quantities, because if I know one of them, I know all of them, essentially. Here I have my transmission line impedances, which I'm going to label ZW. Here's my capital A, B, and C terminals. And lastly, I have a Y connected load. So that's going to be ZY here. and here, and here, like so, with all of these connected together at the load side neutral. So that's capital N. So let's see, for our given information, we're told that ZW is equal to 0.6 plus J 0.3 ohms. We're told that ZY is equal to 12 plus J7 ohms. We're told that our line current, which I'll label on the diagram in just a moment, is 9.6 angle negative 20 degrees amps RMS. And I'm going to say that we're trying to solve for the voltage VAB. So here is my, line current on my diagram. So what I'm going to do now is I'm going to draw a single phase equivalent circuit that is as representative of this system as I can currently make it. Okay. So here would be our voltage VAN. Here's our impedance ZW. Here's our impedance ZY. And I short between my neutral terminals like so. And then here is my line current, IAA. So before I just explicitly show you guys how to do this, does anybody have any thoughts on what our process might be to solve for that voltage VAB? So if we solve for lowercase VAN, we can then do what to that lowercase VAN to get VAB?
Multiply by power or root 3 angle -30.
Positive 30 degrees, but you're absolutely right. So since we have that conversion factor that allows us to go back and forth between a Y connected source and a delta connected source, if we solve for the Y connected source voltages, we can just transform that back into the delta that we're actually interested in. So you're 100% right. That process is perfect. We're just going to solve for this voltage VAN in our single phase equivalent circuit, and then use that to convert back to the delta connected source voltages that we're actually trying to find. Great job. So how would we solve for that voltage VAN?
Add the two together and multiply by the current.
Yeah, so just Ohm's law, essentially. Absolutely right. So we could say that VAN is just going to be our line current IAA times an impedance of ZW plus ZY. Absolutely. So that would look like 9.6 angle negative 20 degrees amps RMS times, I'm just going to add these guys together directly. So 12 plus 0.6 is 12.6 plus J7 plus 0.3 is J7.3 ohms. And when I throw this into my calculator, I get 139.7945. So let's call that 795 with an angle of 10.0865. So let's call that 0.87 degrees volts RMS. And then from here, VAB is just VAN times root 3 angle 30 degrees. So that would be 139.795 with an angle of 10.087 multiplied by root 3 angle 30 degrees. And I get 242.131 and some change with an angle of 40.087 degrees volts RMS, which is exactly the result that we were looking for, according to my previous answer. How would we then use VAB to find VBC and BCA? Somebody else tell me what's going on there. Ricky, you have any thoughts?
Then you could, add 120 degrees to that there, 120.
So you are extraordinarily close. We have a positive phase sequence. That's what it means by an ABC phase sequence. So instead of adding 120 degrees, we should actually subtract 120 degrees because the B phase is lagging the A phase by 120 and the C phase is lagging the by 120. So in all of the problems that I'm giving you guys, we are always going to have a positive phase sequence. And so we should always subtract 120 degrees to get to the next phase result. Okay, so incredibly close, just got the sign backwards. So 40.087 minus 120 gives me an angle of negative 79.913. So that's just going to be 242.131 angle negative 79.913 degrees volts RMS. Subtract another 120, and I get 242.131 with an angle of negative 199.913 degrees volts RMS. And we've worked backwards to essentially solve for our source voltage in this system. So before we move on from this problem, does anybody have any questions or comments or anything? All right, I'll give you guys another minute or so to finish writing stuff down, and then we'll move on to problem 2. Yes, sir.
So we were given the.
You sure?
Yeah.
Okay. Anyone else? All right, so let's move on to problem number 2. So in this problem, we have a balanced delta connected load, which is containing a 10 ohm resistor in series with a 20 millihenry inductor in each phase. The voltage source is positive phase sequence at 60 hertz. It is a Y connected source having a phase voltage of 120 angle 30 degrees volts RMS. And we are asked to determine the line currents in our, the phase currents in our load, as well as the line currents. So once again, I'm going to draw a picture that's trying to describe what's going on. So we have a Y connected source feeding a delta connected load. So here is our Y connected source. Here is our transmission line network. For what it's worth, this wasn't actually mentioned in the problem statement, so we're going to assume that the impedance ZW here is just 0. And I'll explicitly write that down in just a moment. And then we have our balanced delta connected impedance here. So let me take a moment to just write down some information. So we're trying to find VAN, or excuse me, we're not trying to find, we're given VAN is 120 angle 30 degrees volts RMS. We know that the resistance of our delta connected load is 10 ohms. We know that the inductance of our delta connected load is 20 millihenries. And we know the frequency of our system is 60 hertz. So we're going to put all three of those pieces of information together to figure out what Z delta is here in a moment. Ultimately, we are trying to find our phase currents and our line currents. So I'm just going to make a note here. We're looking for IAB and IAA. And I'll label those guys on here. So this would be our current IAB. And for reasons that will become obvious here in a couple of minutes, I'm going to go ahead and label this phase current ICA as well. Then I have my line current, IAA, that we are interested in. So before we can really draw our single phase equivalent circuit, we need to figure out what this impedance Z delta actually is. So can you guys remind me what the impedance of a resistor is?
Just the positive section.
So the impedance of a resistor is literally just the resistor value itself. Doesn't change at all. So we're going to have an impedance of 10 plus J something else, right? So we just keep the 10. Does anybody remember what the impedance of an inductor is? So so the impedance of an inductor is J omega L, where omega is 2 pi times F. So you were the closest, but because we have an inductor, it's not going to be C, it's going to be L, right? So essentially we're just going to do, I've already got the J there, so 2 pi times that L value, right? So 2 pi times 60 times 20 times 10 to the minus 3 comes out to be 7.5398. So let's just call that 7.540 ohms. I'm just going to make a quick note that that is just Z delta is equal to R delta plus J omega L delta. Okay, so in my single phase equivalent circuit, I don't put a delta connected impedance because a single phase equivalent circuit is based on a YY system, right? So what should my load impedance be in my single phase equivalent circuit? So I'm just going to make a note down here. I'm going to call that Z delta Y, meaning I've taken my Z delta and I've transformed it into a Y connected load. What should the value of this thing be, or how do I get that? So if I want to go from delta to Y, divide by 3. So that's literally just going to be Z delta over 3. So that's going to look like 10 over 3 is 3.333 plus J 2.513. Ohms. Okay. So from here, I'm going to draw my single phase equivalent circuit. So here's my VAN of 120 angle 30 degrees, volts RMS. Here's my short circuit for my transmission line impedance, since unless I misread this guy, I don't see it mentioned anywhere. Then this is my Z delta Y impedance of 3.333 plus J 2.513 ohms. And this is the line current that I'm looking for. So I'm not going to be able to put those phase currents IAB or ICA in my single phase equivalent circuit, because those are currents that are flowing through a delta connected load. And as soon as we transformed it into a Y connected load, those currents literally no longer exist. Okay. So we are going to solve for this line current, and then we are going to have to figure out a way to solve for those phase currents. And I can think of 2 different ways we might do it, and so I'll explain to you what both those ways are. We'll wind up getting the exact same result either way, so you can just use whichever one you're more comfortable with. Okay. So how would we solve for this line current IAA? Ohm's law. V over Z is the current that we're looking for. So 120 angle 30 degrees volts RMS over 3.333 plus J 2.513 ohms. So throwing this in my calculator, so I could type the numbers in the right order. I got 28.746 angle negative 7.013 degrees. So a little bit of rounding error, but I would consider those 2 things to be essentially the same, right? I'm off by a millivolt, and I'm off on my angle by 0.003 of a degree. So that's good enough for me. Obviously, we would get IBB by simply subtracting 120 from that negative 7.013 degrees. We get ICC by subtracting 240 from that. I'm not going to bother with that explicitly here because I want to make sure that I've got plenty enough room for what we're going to do next. So let's talk about the 2 different ways that we could solve for that phase current IAB. Okay. So I believe that we have enough information to solve for the voltage V capital A capital N. And then, knowing that voltage, we could multiply by √3 angle 30 degrees to get V capital A capital B. And then we could divide that voltage by our delta connected impedance to find the current. Okay. So this is probably the way that is, to me, it seems the most obvious. It's not quite as efficient as another way, but we'll do this just for the sake of argument so that we can show what's going on, right? So I'm just going to put over here method number 1. Okay. So what is V capital A capital N going to be? Anybody, even you gentlemen in the back that have been answering every question. Yeah, that's what I'm looking for. So we could take that current IAA and multiply it by that impedance Z delta Y. You're 100% right, but that's actually more work than we need to do. I would argue that that impedance is in parallel with that voltage source. So the voltage drop across the impedance has to be the same thing as the voltage drop across the source. So it's just 120 angle 30 without doing any math. Anybody got a beef with that? Right? Because our transmission line network is a short circuit in this case, the source is connected in parallel essentially to the load. Okay. So we could say that VAN is equal to V lowercase an is 120 angle 30 degrees volts RMS, or we could just use Ohm's law. Either way works, but I'm lazy, and if I'm just given the answer, I'm just going to use that. Okay. So from here, how would we get VAB? So it's not an impedance, so it's not going to be just that factor of 3. It's a voltage, so it's going to be the √3 angle 30 relationship. Are we going to multiply it by it, or are we going to divide by it? Multiply by it, okay? So our terminal voltages for, or our line voltages for our load should always be greater than the phase voltages for our load. Actually, when we are trying to go from a Y to a delta, the voltage should always get larger. Let's just leave it that way without getting too bogged down in the line voltage versus phase voltage, this, that, and the other. So we're going to multiply by √3 angle 30. So that's literally just V capital A capital N, just so that I can be more formal about this. √3 angle 30 degrees. And it's going to be something in the ballpark of 208 angle 60, but let me just throw it into my calculator just to be on the safe side. $207.846 with an angle of 60 degrees volts RMS. And then lastly, our current IAB could be found just by using Ohm's law. So that would be VAB over Z delta. So that would be 207.846 with an angle of 60 degrees volts RMS. And here, I'm using the real Z delta, not the transformed Z delta into Y. So that's the 10 plus J 7.540 value. And I got a current of 16.596 with an angle of 22.984 degrees amps RMS. So just as a sanity check here really quickly, I'm going to look at that and compare it to the answers that I got up here. So 16.596, that pretty much checks out. 22.984 degrees also checks out. So let me scroll back down here so you guys can finish writing stuff down. So this is the first method, right? So if we're able to find the phase to neutral voltage across our transformed load, then we can transform that voltage into a line to line voltage, which will be the voltage drop across our delta connected load. And then we just use Ohm's law to find the current, because if we know the voltage drop across one phase of the impedance, then we can just divide by the impedance to find the current flowing through each phase of the impedance, right? So 3-ish steps, nothing horrifying there, I don't think. But there is a little bit better way to do this. So the second method, I'm going to write it over here. And the one that I actually prefer, just because it's less steps, is to apply Kirchhoff's current law to this system at node capital A, okay? So I have a current of IAA flowing in. I have a current of capital C capital A flowing in. And I have a current of I capital A capital B flowing out. So I could write the following KCL relationship. So this is KCL at capital A. Capital A. So IAA was flowing in. Let me continue using the colors and all that shit. So just to be clear here, all I've done is say that the current flowing into that node is equal to the current flowing out of that node, okay? Now, what I'm going to do is I'm going to rearrange things and I'm going to put IAA on one side of the equal sign by itself. So that's my current known quantity, okay? So I would have IAA is equal to IAB minus ICA. Are we all okay with that? So this is another one of those situations like we had on last Thursday's lecture, where it seems like I have one equation and two unknowns, but I know that these two things, IAB and ICA, are related to each other, right? So ICA is 240 degrees behind IAB, right? So IBC would be 120 degrees behind. So CA is 240 degrees behind. So what I really have here is IAB multiplied by a factor of 1 minus 1 angle negative 240 degrees. Somebody throw that into their calculator and tell me what they get. Just that 1 minus 1 angle negative 240. So 1.732 is once again just the square root of 3. So we have a factor of root 3 angle negative 30 degrees in this case. And then rearranging this guy, we could then say that IAB is just going to be equal to IAA divided by root 3 angle negative 30 degrees, where IAA was found up here. So we have 28.746 with an angle of negative 7.013 amps RMS divided by root 3 angle negative 30 degrees. .746 angle negative 7.013 over root 3 angle negative 30. And I got 16.5965, so 16.597 with an angle of 22.987 degrees. Amps RMS. So not exactly the same answer as we got the previous method. This one just has a little bit of rounding error because I didn't use the exact value for IAA, but we can see once again, we're off by just 1 millivolt and 3/1000th of a degree. So we could call these guys equal to each other pretty easily, okay? So either method gives us the exact same result. I personally prefer the second method because essentially what we have stumbled into is a conversion that allows us to go from line currents into delta connected phase currents. So anytime we have a line current, it's going to split by a factor of root 3 angle negative 30. Okay. And then once again, we could get our B phase by subtracting 120 degrees and our C phase by subtracting 240 degrees from here. Okay. Correct. The reason why I'm making that distinction, so a line current into a delta phase current, is because a line current into a Y-connected phase current is literally, there is no transformation. It's the same thing because they're connected in series. So we've stumbled into something here. So we learned earlier on, I guess this would have been either last Thursday or last Tuesday, that in a delta connected system, our line voltage and our phase voltage are literally the same thing. Well, in a Y connected system, our line current and our phase current are the same thing. And to go between those quantities in the opposite type, we're just going to be multiplying by an angle of root 3 and plus or minus 30. It's positive 30 for voltage, it's minus 30 for current. And again, you don't have to memorize all of these transformations and how to apply them and all of that kind of stuff because they were really easy to derive, I think. Just for what it's worth, we derived this one by applying KCL at that node. To derive the voltage relationship, we just did KVL around that left-hand loop. The only transformation that you really kind of have to know in order to analyze these systems is how to go from a delta connected impedance to a Y connected impedance. That's the only one that takes any time to derive. And that's literally just dividing by 3. So, all right. Any other questions about this particular problem? Okay, so the next problem is the hardest one I've asked you guys to do by far. Okay. So we have a Y connected voltage source. And we are told what the line voltage is. And then we have two loads. One is a Y connected load having an impedance of 10 plus J3 ohms. And the second is a delta connected load having an impedance of 9 plus J6 ohms. In addition, we also have a transmission line impedance of 0.05 plus J 0.02 ohms, and we're asked to determine our line currents and our phase currents through each load. Okay. So one of the hardest things about a problem like this is literally figuring out how to draw this damn thing. Okay. So this is the first time we're seeing two different loads connected in parallel. So I want to explain how I choose to draw this, and then we can go from there. All right. So starting off, we have our Y connected source. So here's A, B, and C. And for what it's worth, we are told what this line voltage is here, VAB. So I've gone ahead and indicated that on my figure. Now I'm going to put in my transmission line network. A, B, and C. So here's my impedance of ZW. ZW, and yet another ZW. Okay. And then lastly, I have to figure out how I'm going to do my two loads. Okay. So I'm going to start by putting in my delta connected load, right? So in my delta connected load, I should have an impedance Z delta connected between the A and B terminals, an impedance of Z delta connected between the B and C terminals, and an impedance of Z delta connected between the C and A terminals. So something like this. And for reasons that'll be obvious here in a moment, I'm going to make this guy kind of big and put that last Z delta over here. Okay. Now I'm going to put in my Y connected load. So I'm just going to choose a point here in the middle and call that my capital neutral terminal. And I know that for a Y connected load, I should have an impedance between the A terminal and that neutral terminal. Between the B terminal and that neutral terminal. And between the C terminal and that neutral terminal. So this is how I would depict a parallel delta and Y connection. Okay. For what it's worth, let me mention this real quick and then I'll happily answer your questions. It literally can never get harder than this. And what I mean by that is if we had multiple Y connected loads, we would just lump them all together and have an equivalent impedance ZY to worry about. If we had multiple delta connected loads, we could just lump them all together and have an equivalent Z delta to worry about. So it literally, this is as hard as it can possibly be because I only have those two different options and they're both represented here. Ricky, what was your question?
The impedance in between
That bottom one should be a Z delta. Thank you for that. Yes, that's just a brain fart on my part. Thank you very much for that. This guy should be Z delta. Okay, so all I'm going to do here is the same thing I've done on the last couple of things. I'm just going to write down our known information, identify what we're trying to solve for, and then we're going to try to kind of sort stuff out. Okay, so we know that VAB is 400 angle 45 degrees volts RMS. We know that ZW is 0.05 plus J 0.02 ohms. We know that ZY is 10 plus J3. And lastly, we know that Z delta is 9 plus J6. Once again, we have a delta connected load, and we're going to try to use our single phase equivalent circuit to solve for things. So what is the Z delta Y going to be in this case? So converting that delta impedance into a Y impedance. Divide it by 3. So what's 9 divided by 3? 3. What's 6 divided by 3? 2. So this is just going to be 3 plus J2 ohms. So from here, let me identify the things that we are interested in. We're trying to determine our line currents. So I'm just going to represent that by a single line current, IAA, like so, because we know if we know this one, we can get the other ones very easily. And then I'm going to have my phase currents, okay? So this is going to be my phase current, IAB, and this will be my phase current, IAN, and we'll see in a couple of minutes. I'm going to wind up using this guy, ICA as well. Okay. So if I were to draw my single phase equivalent circuit for this guy, it would look something like this. So here's the voltage VAN, which I currently do not know. Here's my impedance ZW, which is a known quantity. Here's ZY between my A terminal and my capital and neutral terminal. And then over here to the right, I'm also going to have Z delta Y, my converted delta connected load impedance. Now I'm going to indicate on the graph which of these quantities that I'm trying to solve for can actually be determined just from my single phase equivalent circuit. That would be my line current and the phase current through my Y connected load. My phase current through my delta connected load, once again, I can't get directly from my single phase equivalent circuit. So I'll have to use either method 1 or method 2, like we discussed earlier. So I believe that in order for us to solve for any of those currents that we're interested in, we need to know what our phase voltage of our source is. So how would we go about finding VAN? And recall that we know what VAB is.
Is there a relation between VAN and VAB?
Yeah, it's literally the first thing we talked about today. Yep, divide VAB by √3 angle 30 to get VAN, 100%. So 400 angle 45 degrees volts RMS over √3 angle 30 degrees. I get to be 230.940 with an angle of 15 degrees volts RMS. And for what it's worth, I'm going to store this in my calculator as actually X so that I don't run into any rounding error in this particular problem, just because I'm worried about it compounding too much. So anybody have any questions, comments, or concerns about how we got lowercase VAN, our phase voltage of our source, by knowing what lowercase VAB, the line voltage of our source was? That's literally just that conversion factor that we've been using, okay? All right, so from here, I am open to suggestions about how we might solve for either of those two currents.
Solve for current AA
Okay, how do we do that?
with, its current IAA is equal to VA and divided by delta one.
So the current IAA kind of represents like the total current leaving that source voltage. So if I were going to solve for that one directly, I would probably wind up using the equivalent impedance of everything the voltage source sees. Does that make sense? Okay. So the equivalent impedance is just ZW in series with the parallel combination of Y and Z delta Y, right? So this would be 0.05 plus J 0.02 plus, let's see, Z delta, or excuse me, ZY, goodness, is 10 plus J3. Z delta Y is 3 plus J2. And then I would have 10 plus J3 plus 3 plus J2, like so. And I'm going to throw that into my calculator real quick. And I got 2.4056. So let's call that 2.406 plus J 1.345 ohms. And I'm going to store this in my calculator as Y. Before we move on from here, did anybody else get a similar result for the equivalent impedance? For what it's worth in polar form, that's 2.756 angle 29.205, depending on what your calculator's set for. Ultimately, yes, but I want to just confirm that this ZEQ is right before we move on to that step. just because it was something long to put in my calculator, so I might have made a mistake. I just want to make sure that you guys are getting a similar result. Got a thumbs up over here. Okay. All right, so Salvador, I believe your name is. Do you have a suggestion on how we might solve for IAA since you brought it up here?
We have a BAN, we have the DEQ, so we do BAN, divided by DEQ.
Yeah, absolutely right. Just good old Ohm's law. Okay. I'm going to do that calculation over here on the left for what it's worth. And I'm not going to bother writing out all the numbers since they're available right over there. And I stored them in my calculator for a reason. So it's what I have in my calculator as X over what I have in my calculator as Y. And I got that to be 83.795 and some change with an angle of negative 14.205. And I'm going to store this as Z. And just as a sanity check, looks like I got the right result. So, knowing that current IAA and knowing the voltage V lowercase a lowercase n, how could we then determine I uppercase a uppercase n?
Or can we do the current division for that?
We absolutely could, yeah. So I uppercase a uppercase n is just going to be IAA times 1 over ZY divided by 1 over ZY plus 1 over Z delta Y. And I'm just going to throw the numbers as appropriate here into my calculator. So that's what I have stored as Z multiplied by 1 over 10 plus J3 divided by 1 over 10 plus J3 plus 1 over 3 plus J2. So let me just double check here. ZY is indeed 10 plus J3. I'm finding a current through that guy, so that's why the reciprocal's in my numerator. Both parallel paths are in my denominator. So that seems legit to me. And I got 21.6915, so let's call it 692 with an angle of negative 1.552 degrees amps RMS. And I'm going to save this in my calculator as T in case I need it later. So the last thing that we're looking for, if I can scroll up here for a smidge, is how to find that current IAB. So just for what it's worth, we could use the current IAN, capital A, capital N that we just solved for to get the voltage V capital A, capital N, convert that into a line voltage. So V capital A, capital B, and then divide that voltage by Z delta to get the current that we're looking for. Or we could effectively perform KCL up at this node right here, like we did for method 2. The only real difference that we would see, so we're not going to get this exact thing where it's just going to be IAA over root 3 angle negative 30, because we have that extra term of IAN that is also leaving, okay? So if we do that KCL method, it's going to be a very similar result, but it's not just going to be the line current over √3 angle -30, because we have that other current flowing out of that node as well. Yes, sir.
For the most part, the thing that was happening, one thing I don't understand, whenever we made the second graph, why did we do where did the D delta Y, come from? Why wasn't it included, you know,
So why isn't it included up above?
why is it like, on the second graph that we made?
Right, okay. So to answer that question, let me go back to the previous example problem, okay? So in this previous example problem, we only had delta connected impedances, and our single phase equivalent circuit is used when we have a YY system, right? So effectively, I took those Z deltas, I converted it into Z delta Y, which places that new impedance between the capital A terminal and the capital N terminal so that I can put it in my single phase equivalent circuit. Okay. I did the exact same thing in the second problem. So I have a delta connected impedance of 9 plus J6. I converted it into a Y connected impedance by dividing by 3. And so now I have two Y connected impedances in parallel. So anytime I have a delta connected impedance, I need to convert it into a Y connected impedance so that I can put it into my Y connected single phase equivalent circuit. So I want to use the method 2 here with the KCL just because I find it to be a little bit easier on my brain. I always just try to go back to fundamentals whenever at all possible. So I'm just going to write my KCL equation up top here, and then we'll manipulate that in just a second, right? So I have a current of IAA flowing in, and then I'm going to have an IAB minus an IAN minus an ICA. And so I can see pretty easily that I'll have IAA plus IAN is equal to IAB minus ICA. Does my KCL relationship make sense here? So from here, now I can apply that relationship because I know that IAB minus ICA is just IAB, what I'm looking for, times √3 angle -30 degrees. So I'm just going to scroll down here. I'm going to say IAA plus IAN is equal to IAB times √3 angle -30 degrees. That's from the result of our last example problem. And from here, I can say that IAB is just IAA plus IAN over √3 angle -30 degrees. And IAA is in my calculator as Z, IAN is in my calculator as T. So I'm literally just going to do Z plus T divided by √3 angle -30 gives me a result of 60.661 with an angle of, positive 18.387 degrees. Amps RMS, and let me just double check that guy. Oh, I got something vastly different there. Let me double check some things. So my IAN is right. My IAA is right. Did I mess up on a sign up here in my KCL relationship? Let's double check that. So let me just start from scratch here. I think this is where my issue is, okay? IAA is flowing in. This is what I get for trying to be fancy. ICA is flowing in. IAB is flowing out. And IAN is flowing out. Okay, so realistically, I would get IAA minus IAN is equal to IAB minus ICA. So I literally just need to go back and change that sign. My apologies. So Z minus T over root 3 angle 30. And we get 36.2635. So let's call that 264 with an angle of negative 48.542, actually 543 degrees. Amps RMS. And that does indeed oh, son of a bitch. Now I forgot to do the minus sign on that 30. So that angle is wrong. I'm just making all kinds of mistakes doing this simple math here. That angle should be positive 11. Sorry. 457. That time it was a calculator error, or no, it was a user error in as much as I put it in wrong, but yeah. Okay, sorry about the hiccups there on solving for that current IAB. The process was the same. I just couldn't do KCL to save my damn life and then accidentally flip the sign on the 30 degrees things. So process is correct. My ability to do math in my calculator, highly suspect at the moment. Sorry about that. Okay, this is the last thing that I wanted to talk about for today. So we finished up the ICA. Please turn it in. We've still got 23 minutes left of class. So if you guys have any questions about anything here, any of the homework assignment or anything like that, by all means, please ask.